This video addresses Monte Carlo simulations. We'll look at some basic statistical tools and try to understand the basics of the Monte Carlo simulation. So the Monte Carlo simulation is a probabilistic model involving an element of chance. The advantage is that we can determine approximate results of an indeterminate system or stochastic system. These are quite often easier to develop, although not all the time. So disadvantages, these simulations are expensive in time, or they may take a lot more to develop. So initially they seem like they're easy to develop, but as we try to add more accuracy to the model, it can become very more difficult. All right, and the big disadvantage is that it's virtually impossible to test every possible alternative. So we actually have to run, and that's what we mean by expensive in time, is we have to run these simulations thousands or even millions of times to try to get a best solution. But that best solution could be way off at certain times. Since the simulation has an element of chance, you're just never quite sure what your results, how your results are going to match the real world system. All right, so to start with, Monte Carlo is basically randomness. And computers are actually deterministic things. They're not random. And so they do have a random function, but technically the rand function is what we call pseudo-random. And what that means is that the values appear to be random. This is a special function where when you run it and you ask it to give you multiple values, it appears to be random. So if you run it once, you get some numbers, and then if you run it another time, you get completely different numbers. However, this function has what they call a seed or a start point. And if you use the exact same start point, then it will generate these exact same numbers, okay? Because these are not actually random, they're deterministic values. But the way it's generated, if you generate with a different seed, then your numbers will be different. But you can actually duplicate those results because the random function is actually deterministic. So you always want to generate starting with a random seed value. And so a lot of times what we do is we use like the current time, like this exact second or something, as a seed value to start off the random function. Also on certain systems like the Unix systems, like the Owens supercluster, they actually have special programs built into the operating system to generate random seed values. So if you don't specify it, it will actually set those values for you. All right, so what we want to do is we want to try to generate random values, but these a lot of times we need to get, even with these random values, we want to get a uniform distribution over an area or a matrix. So if we kind of take a look here, what we're doing is we're picking points in this area. So we have this defined area, and we're trying to randomly go through here and pick points. And so as you can see, it's going through there. But one thing, I'm going to stop it here for a minute, and just, you see there's areas, there's gaps in here. So this random, this pseudo random thing, there's areas where there's just nothing. All right, and so there's kind of these sort of almost like a maze sort of thing where as you go around here that some areas are completely untouched as you add these. And so to try to incorporate as much of those holes as possible, we need to add more points and more points. But even so, there's always going to be some areas that just seem to be missing there. All right. So that's why we need so many points. So if you see here, I'm using the rand function to build a random matrix. Now the random matrix, or the random function, generates a value between 0 and 1. So it generates a random value, or pseudo-random technically, a pseudo-random value between 0 and 1. And so what I'm doing is I'm building a matrix, and in this example that I've got plotted here, I have 100 values in the x direction, and for every one value in the x direction, I have 100 random values between 0 and 1 going here. So I mean, if you wanted to try to count all these dots, there's 100 dots all along here. And so this function here gives us a fairly uniform distribution, but again, you can see there's like some areas there that seem to be a little bit light, like there's holes in this random area. All right, so once we have that, then we can look at trying to find, say, the area under the curve. All right, so we've already done this using a deterministic method, right? Using Euler's method, we've been able to find the area under the curve. And so what we're going to do here today is we're going to try to find the area under the curve by throwing darts. We're going to use these random values and throw darts here. So the first thing we need to do is just kind of want to remind you about calculating an area. So if I have the area of a rectangle, I could calculate the base times the height. If I have the area, if I wanted the area of a triangle, I would have 1/2 base times the height. If I wanted the area of a circle, it would be pi times r squared. Right. So these are known areas. There's no randomness or anything. These are known values. And what we're going to try to do is come up with an area, or come up with the area within a triangle or whatever by doing that. So we're going to work with a triangle. So I want to remind you of the slope of a line. Okay, and you'll see why here on the next slide. But the slope of a line, we need 2 points. Y1, x1, y1 value, and an x2, y2 value, and then we can find the equation of a line. All right, so there's a couple of different forms for it here, but the idea here is what we're going to do is we're going to use the random function to generate this matrix, and then we're going to basically use all these point values. Think of it as throwing darts. So we want to find the area within this triangle. So here's a triangle now. So we want to try to find the area within this triangle. So we know, based on the units given here, that this triangle, the first point is 0.20. The top point is at 1 and 0.8, and the third point here is 1.8 to 0. And so we know that the width is 1.6, we know that the height is 0.8, we know that the area of a triangle is 1/2 of that, And so we can calculate then that the area of this triangle is 0.64 units. So if our units are meters or whatever, it would be actually meters squared. All right, so given that, so we know that, we can use the equation of the line. So we actually have two lines here we're going to have to find. The one line is from 0, from basically, well, x equals 0.2 to x equals 1. And so we got y is equal to 0 and 0.8 for that line. And then we have another line. And so what we're going to do is we're going to throw darts. And if the dart falls inside of the triangle, then we're going to count that as a hit. And if it falls outside, then it's going to be a miss. And so we're going to calculate the equation of the line for the first, for the left line, and then also the equation for the line of the right line. And then we're going to run this simulation. All right, and so this simulation is going to say, if we're going to run this for so many values, and then for each value we're going to have to ask the question, is this value less than our line? And if it is, then we're going to increase the hit. Alright, so here is my code. Again, we're going to start off by simply clearing the figure, or clearing all the variables and clearing the figure. And then I'm just going to plot a point here. Okay, so I'm going to plot the top point, which is at y, which is at the x value from 0 to 1. Actually, this is the line. I'm sorry. This is the line here from 0 to 1. And the x, my 0, 0, and 1, 0. I'm just plotting some lines here to get the plot started. Okay. Then I'm setting my values. Okay, and I'm going to throw 100 darts at this. Okay, so I've got a total number of darts, and then I've got my area of the triangle. Okay, so here I'm just calculating x max and x min is going to be the, this is the area of the rectangle. Said that wrong. So we're going to take the area of the rectangle. That's this matrix. Okay, so here is our matrix. Okay, so we're going to take this matrix, and the first thing we have to do, we're going to create this matrix, and we are going to basically we're going to build a matrix of this rectangle here, and we're going to throw darts in here. So all the little dots you're looking at are these darts. These are where the darts hit. So we have this rectangle, and we know the area of this rectangle. Now we have to scale this rectangle so that our triangle, see, we're trying to find the area of the triangle. So we want to put this triangle must fit inside of the rectangle. And so the first thing I'm going to do is calculate the area of my rectangle. So my rectangle is going in the x direction, it's going to 2, because if you look at here, right, in the x direction, the triangle was going to 1.8. And so I'm going to run it just a little bit beyond that, because I want to get the area of the entire triangle. I've got to make sure that the entire triangle fits. So x, I'm going to run x from 0 over to 1 over to 2. And I'm going to run the magnitude. What did I run the magnitude is? The magnitude is 1. So or I'm sorry, the y max was 0.8 because my triangle went up to 0.8. So I'm capping it right there at 0.8. Okay, because that was the height of my triangle. But I ran the area. You could run y up to 1 also if you wanted. We can maybe do that here in a little bit. But what I'm going to do is I'm going to throw 100 darts at this, and I'm then going to look at the equation of the line. And if the equation of the line, I'm going to randomly generate an x and a y value. Okay, so here I'm randomly generating an x and a y value. And then I already calculated these equations, right? So here is the equation. Here is the equation for the line going down on this side. And on the previous slide is the equation for the line of the triangle going up. All right. And so what I'm going to do is I'm going to randomly generate this function, and then I'm going to use an if statement, and I'm going to say if this random value, I'm going to evaluate this random value of x times the slope and of my line, and I'm going to find out whether it is above or below that line. And if it's above it, I'm going to color. If it's above it, I'm going to color the dots green, and if it's below it, I'm going to cover them. Or excuse me, if it's below it, then it's in the area. I'm going to color that green. So if it's a hit, I'm going to make that green. If it's a miss, this is a miss, I'm going to color that black. All right, so I'm just going to run this here. We'll see what this does. And so what you can see here is here are my two lines. And what it's doing here is the black were the misses. Those were outside or above the line, and the greens were below the line. Now remember, we already calculated the area of this triangle, and when we calculated the area of this triangle back on the main slide, we found that the area of this triangle was 0.64. But when I did this random Monte Carlo solution, my answer is 0.76. All right, so that's not very accurate. So let me run it again. Okay, so that was a 0.76, 0.768 was the value. So I'm going to come back over here. I'm going to run it again. And now I've got 0.800. All right, that was even worse. Let me run it again. Now it's 0.816. Okay, let me run it again. Now it's down 0.736. Now that's the closest, but it's still quite a ways off. However, if I come over here and instead of doing 1 dart or 100 darts, let me do 300 darts. Okay, so I'm going to change that to 300. Okay, and I've got to scale this value. And so now I've done 300, and there it's almost it's 0.789 again. All right, and actually this solution is actually going to it's going all the way to 0, so my solution isn't quite right. I was wondering about that, so I should be subtracting off of here. Let me see, my equation of the line for that one. It should have been, yeah, 1 times x minus 0.2. So let me run this again. Okay, so this value is a little bit better because I didn't redraw my line, but it's down to 0.66, okay? But let me go back to 100 then. All right, so if I do 100 darts, I get 0.592. If I run it again, I get 0.592 again. That was weird. Oh, now I'm down to 0.48. Now I'm up to 0.576. Alright, but if I do 300, if I do 300 darts, takes longer. See how much longer that took? But the value, look at that value. That value is a lot closer. Alright, because remember our value, our actual solution we calculated was to be 0.64. So when I ran it that time, I got 0.635. So that looks pretty good. Let's run it. I make no changes, run it again. And oh, well, look at that, right on, 0.64. Let's run it again. Oh, now we're down to 0.613. So you see the Monte Carlo method is not quite as is not going to be accurate all the time. Sometimes you may get the exact solution, but you got a bigger chance of not getting the exact solution. Where with a deterministic system, you know, if you do use Euler's or some other method, you can get reliable results and the same solution every time you run the simulation if you don't change any code. But here, every time, even though I'm not changing the code, every time I run it, I'm getting different values. There I'm up above 0.661. All right, run it again without making a change. 0.651. All right, so every time you run it, you're getting a slightly different answer. Now, as you increase your number of darts, so I'm at 300 darts, if I go to, say, 600 darts, it's going to take twice as long to run, all right, and my value was still supposed to be 0.64, and it's at 6.27 here, so I'm still off. And it's taking longer and longer to run as I increase my number of darts. All right, and at this point I'm only doing 600 darts. So and I got an exact solution there again, up to 3 digits at least. All right, as you can see here, as we run this, now we're way down to 0.568. So that is the issue with the Monte Carlo method. There's always a question about how accurate your results are.